So let's continue our discussion of acids and bases. We're going to use the Bronsted-Lowry definition of acids and bases in order to be able to talk about the relative strength of acids and bases. So you may remember from first semester that when we talk about a strong acid or a strong base, we are not discussing how dangerous that acid or that base is. Fundamentally, what we're talking about is how strong an electrolyte the acid or the base is. So how many ions do we get when we dissolve that acid or that base, say, into water? And so if we use the Bronsted-Lowry definition of acids and bases, we can think about that process as basically a reaction, and we can think about what is happening in terms of being able to either donate a proton or accept a proton. And so if we think about that acid-base reaction as basically a competition for a proton, that allows us to talk about this idea of strength. And so we're going to be thinking about essentially a tug of war between both sides of the reaction, or between different things on either side of the reaction, I guess I should say. And so we're going to use this sort of generic looking acid-base reaction to talk about this relative strength idea. And so here A and B are just two ions of some sort, two anions that both can form acids when they have a proton on them. And what we're going to look at is what's happening in this sort of tug of war in this equilibrium reaction. So on the reactant side, we have HA, we have an acid there, reacting with B minus, so some anion. On the product side, we then have A minus, which is the conjugate base of our acid HA, and we have HB, which is the conjugate acid of our anion B minus. So we have two conjugate acid-base pairs that we're talking about in this equilibrium reaction. And so we can look at how they, sort of who's going to win the tug of war in this acid-base reaction. So let's start with an example. If we look at HBr, so HBr dissolving in water essentially, here we would be looking at HBr reacting with water, because remember, when we dissolve something like HBr in water, we don't really just have H plus floating around. What happens is that H plus is going to attach itself to a water molecule to create a hydronium ion, and it's really hydronium ion that we have in this reaction. And so the equilibrium reaction that we would want to look at here is what we have set up. We have HBr going to Br minus. That HBr, the proton on the HBr then is donated to a water molecule, which turns into a hydronium ion on the product side of the reaction. And so again, we have two conjugate acid-base pairs. We have HBr as the acid on our reactant side, Br minus as its conjugate base. That's one pair. Then we have water acting as a base on the reactant side, and we have hydronium ion as its conjugate acid on the product side. And so if we look at this reaction experimentally, hopefully you already remember this, HBr is a strong acid, and so experimentally this equilibrium lies very, 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 very far to the product side. And so we could say that our K is very big for this reaction. And so I've drawn the equilibrium errors sort of disproportionately here. So the forward is basically mostly what's happening, even though this is technically an equilibrium reaction. And so because experimentally we know that this is essentially completely products, what that tells us then is that HBr is really good at donating its proton. In fact, it's much, much better at donating its proton than the hydronium ion is. Because if we look at the reverse reaction, it would be hydronium ion that was donating the proton, Br minus that was accepting the proton. Right? And so we can compare the strength essentially of HBr and the hydronium ion. So this tells us from this experimental data that in terms of acid strength, HBr is a better acid. It donates a proton far better than the hydronium ion is. And I've used much greater than symbols here because it is significantly better, because this is almost entirely on the product side. The other thing that this tells us is about the base strength. And so if we look at our two bases here, water is actually much better at accepting a proton than Br minus is. And so in a sense, water is winning that tug of war for the H plus ion over the Br minus ion. And so the base strength from a Bronsted-Lowry definition is essentially going to be much stronger for our water than it is for the Br minus. And so in terms of base strength, we would rank the water as being a better base than the Br minuses. Okay, so if we take this as a general rule and use this example, the general rule is that reactions tend to lie in the direction of the weaker acid and the base. And so that sounds a little strange because of what the definition of the strength of an acid is, because I've said we're going to deal with this like a tug of war. But essentially what that ends up meaning is that your reaction is going to be on the side where you have a weaker acid and a weaker base, simply because to be weaker in the sense of acids and bases means that there's going to be more of you when you get to your equilibrium reaction. So if you have a weaker acid, it's not as good at donating that proton, and so you're going to have more of the molecular acid form when you get to equilibrium. If you have a weaker base, it means it's not as good at accepting that proton. And so again, you're going to have more of that when you get to the equilibrium mixture. And so when you have an equilibrium reaction, an acid-base equilibrium reaction, when you get to equilibrium, you're going to have mostly the weaker acid and the weaker base. And so if we look at our example here, that holds true, right? When we come to equilibrium here, we end up having almost entirely products. And if we look at the way that we ranked our strength of acids and bases, we said that Br minus is our weaker base and hydronium ion is our weaker acid. And therefore, when we come to equilibrium, we're going to have mostly those in our equilibrium mixture. And so if we can take this observation and we can understand that we're going to have weak acids and bases at equilibrium, we can basically use experimental information about these equilibrium reactions to rank the strengths of acids and bases. And so we can look at a number of different equilibrium reactions. We can say, okay, in this case, it lies towards the product side. In this case, it lies towards the reactant side. By doing experiments, by measuring what our equilibrium constant is, and from that, we would be able to rank the strengths of acids and bases. So for example, if we look at acetic acid in water, so again, we're going to compare it to water in this case. If we put acetic acid in water, we know from first semester that acetic acid is what we would define as a weak acid. And so when we put acetic acid into water, we get some ion, we get some of the acetate ion, but mostly it stays in the acetic acid molecular form, essentially. So mostly we have reactants as we look at this equilibrium reaction. And so again, we have two acid-base pairs. So we have our acetic acid and the acetate ion as its conjugate base, and we have water and hydronium ion as a conjugate acid-base pair as well. So we have two acid-base pairs. We're going to look at that equilibrium and look at what this means in terms of the acid-base strengths. So we'll be comparing the two acids in this reaction to the two bases in this reaction. And so if we do the experiment here and we measure which form the acid-base pair of the acetic acid and the acetate is in, what we end up finding out is if we have 0.1 molar acetic acid, only about 0.1% of it is ionized. And so we mostly have reactants when we come to equilibrium. And so what that tells us then, if we mostly have reactants, again, remember the equilibrium is going to lie in the direction of the weaker acid and the weaker base. And so what that tells us is that acetic acid is actually a weaker acid than hydronium ion, because hydronium ion is better at donating that proton than the acetic acid is. And since it is better at donating the proton, we're going to mostly have acetic acid in our equilibrium mixture. So the stronger acid here is hydronium ion. In terms of base strength, it tells us that water is actually our weaker base. And so what that means is that the acetate ion is better at accepting a proton than water is. And so we're going to lie in the direction of the reactants in this case, as we know from knowing that it's only about 1% ionized or 0.1% ionized. And so we mostly have reactants here. Okay, so if we put those two observations together and put them into ranked order, what we can end up saying then is we know that of these three acids, HBr is our strongest by a pretty significant margin. Hydronium ion then comes next, and acetic acid is actually the weakest of the three that we've looked at. Our base strength essentially goes in the opposite order. So our weakest base is going to be the acetate ion. So the conjugate base of our weakest acid is our strongest base, and that's a very important observation. Br minus is going to be our weakest base because HBr is our strongest acid. And so HBr is very good at donating that proton. Br minus is not so good at accepting a proton. Okay, so if we go and try to look at what happens with the strong acids, you'll remember the strong acids from first semester. We're going to compare HI, HBr, HCl. So if we look at that, if we have this in aqueous solution, as we said in first semester, these are all basically 100% ionized in water. So we have completely products. You'll notice I haven't even used an equilibrium arrow for these reactions because they are essentially completely products in water. And we call this the leveling effect, basically. What that means is if we try to do this comparison in aqueous solution, there's no way to make the comparison because they're all the same. And so one way to deal with this is to use a different solvent. If we use a solvent that's less basic than water, we can compare those strengths. And so one thing that we can do is we can use pure acetic acid. So notice this is not an aqueous solution. This is liquid acetic acid. And so if we try to dissolve HI, HBr, HCl in pure acetic acid in the liquid form, what we will observe is that, in fact, in this case, HI is going to be more ionized, so we have more ions in solution than HBr. HBr is going to be more ionized than HCl. And so now we can make this comparison. Even though they're all strong acids in aqueous solution, we can rank them now by making the observation in pure acetic acid. And so the acid strength then ends up going HI, HBr, HCl, with HI being the strongest and HCl being the weakest of these three strong acids. They're all strong acids. You still need to memorize the strong acid list. That is not going to change, but we can in fact put them in rank order by comparing them in acetic acid. That also tells us what the base strength is. And so the strongest of the acids is going to have the weakest conjugate base, and so the weakest of our three conjugate bases here is going to be I minus. The strongest is going to be HCl, or sorry, Cl minus. And so Cl minus is better at accepting a proton than I minus is. And again, we can deal with that by looking at the equilibrium and by realizing that we're going to have essentially the opposite ordering for the conjugate bases as we have for the acids. So again, I'll point it out again. The conjugate base of a strong acid is a pretty weak base. The conjugate base of a weak acid is going to be a strong base. And so because these pairs are related to each other, if one of the two pairs is strong, by definition it means the other one needs to be weak. And so if we look at a comparison of this across a lot of different acids, essentially what we can do is we can rank them, and we can go through and do the experiments. We can rank them in order. You'll see at the top of this list we have the strongest acids listed. At the bottom of this list we have the weakest acids listed. And notice that we're talking about conjugate acid-base pairs here. So each of these differs by one proton. Even the sulfuric acid, which has 2 protons, when we talk about its acid strength, we're actually just talking about the first proton being released, not both protons. What that also tells us then is the rank order of our bases. And so the weakest of the bases that we have on this list is going to be ClO4 minus, and we get stronger as we go down the list. Because again, conjugate acid-base pairs, if one of them is stronger, the other one is going to be weaker, and we can do this in order. And this chart would have been built experimentally. You would have looked at different experiments, looking at the equilibrium of all these different kinds of things in equilibrium. And again, as a reminder, the reactions tend to lie in the direction of the weaker acid or the weaker base. And so if you set up an equilibrium reaction, if you can tell which is the weaker acid and which is the weaker base, whether you have reactant side or product side, that's going to tell you if your equilibrium is on the reactant side or the product side. And if we go back to our equilibrium knowledge, that's also going to tell us how big the equilibrium constant is. And so you can use that as a pretty quick example there. So if we think about this example, we can use that information to tell us which way it's going to lie. And I'm going to leave this as a question for you to complete, and so we'll stop there for now.